Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all in today's session. To access the notebook for today's session, you can access course page on my personal website arifpat.me. The other way is to download the notebook files from course GitHub account arifpucit, and all the notebooks for this course are housed in this public data science repository. Well, this is the Jupyter Notebook dashboard running locally on my machine at port 8888, and here is the notebook for lecture number 6.25 of the 6th module Machine Learning for the course titled Tools and Techniques for Data Science. In today's session, I will just be setting the stage right, my dear students, for our upcoming sessions in which I will be covering the family of naive-based classifiers, that is Bernoulli, multinomial and Gaussian. Today's session will be a comprehensive recap of the probability concepts required to understand Bayes' theorem. Okay, so here is the learning agenda for this notebook. After a brief overview of classical and empirical probability, some important terms related to probability and types of events, I will be explaining marginal, joint and conditional probability with lots of examples, theoretically as well as using Python code. If you just want to revise a specific topic, feel free to jump to that one by clicking the timeline in the description box below. But I strongly recommend to go through with this video from start to end to have a crystal clear understanding of all the prerequisite concepts required for understanding the family of scikit-learn's naive Bayes classifiers. If you are not new to probability, you may adjust the payback speed to 1.25 or maybe even 1.5. I wish you a happy learning. Well, my dear students, instead of straight away jumping on to understanding and practically implementing naive Bayes classifier, I will spend this session on the math behind this classifier, which is very important in machine learning. You might have seen my two videos on descriptive and inferential statistics. Well, descriptive statistics is used to describe, summarize and present different data sets through numerical calculations and graphs. In my descriptive statistics session, I think I have practically covered the three measures of center, mean, median and mode, four measures of spread, range, IQR, variance and standard deviation, and two measures of asymmetry, that is skewness and kurtosis. Well, the second video is on inferential statistics, that is used to make predictions and inferences for an entire population based on sample data from that population. The inferential statistics session was also divided into further three sessions. The first session covered basic probability concepts, the second covered hypothesis testing, and the third was a journey from variance, covariance, correlation to regression. Well, I have just given you this intro of these two videos so that interested students can go through these as well if they want to. However, today's video will be a precise but comprehensive session on all the probability concepts like marginal, joint and conditional probability that I think are a must to know in order to understand Bayes' theorem, which makes the basis of the naive Bayes classifier. And of course we will do this lots and lots of examples for our crystal clear understanding. Let me start with the comparison between theoretical or classical probability versus empirical probability or experimental probability. My dear students, in general, probability is defined as the likelihood of occurrence of an event. For example, predicting the outcomes for tossing of coins, rolling of dice, or drawing a card from a pack of drawing cards, playing cards. And we normally say when the probability of something approaches 1, then it means it is very likely. And when the probability of something approaches 0, then it means that it is very unlikely. Excuse me. Well, this classical probability is used when you do not have past data and is based on theoretical assumptions. It is calculated as a ratio of the number of favorable outcomes of an event to the total number of outcomes in sample space. You can consider a scenario of tossing a coin 100 times without performing the experiment. The classical or theoretical probability of getting ahead will be 0.5. Empirical probability, on the other hand, is also called experimental probability, which is used when you have past data available with you. It do not use a sample space, rather use frequency distributions. It is calculated as a ratio of the number of times a particular event occurs to the total number of trials. Suppose we actually toss a coin 100 times and get say 60 times heads and 40 tails. The empirical or experimental probability of getting ahead will be 0.6. And my dear students, as we increase the number of trials, say from 100 to 10,000, the result get close and close to 0.5. And this is what is called the law of large numbers, which states that the more experiments we run, the closer we tend to get to the classical probability. I hope this makes sense. And before moving ahead, let me describe some important terms that you will come across while studying probability, like random experiment, trial, outcome, sample space, and event. Well, an experiment is called random experiment if it satisfies two conditions, and the first is it has more than two possible outcomes, and second is that it is not possible to predict the outcome in advance. An example of a random experiment is tossing a coin. The next term is trial, which refers to a single execution of a random experiment. For example, this image shows over here two trials of tossing a coin. The sample space is a set of all possible outcomes that can occur as a result of the trial or the random experiment. A sample space for tossing two coins or tossing a coin twice is head head, head tail, tail head, and tail tail, which can be represented as a list, as a table, or as a tree diagram. The fourth term is outcome, which is the result of a single trial of a random experiment. And in this example of tossing a coin twice, the outcome can be one of these four values in the sample space. And finally, an event is a subset of sample space and can include a single or multiple outcomes. For example, in this random experiment of tossing a coin, there can be many events like getting two heads having a single outcome, and another event can be getting at least one head having three outcomes. And of course, a random experiment can also have many events. Well, to have a clear understanding of these five terms, let me give you another example of rolling two six-sided dice as shown over here. And this time we have two dice and we have rolled them once. So the trial is once. This above table show the sample space, which is a set of 36 possible outcomes that can occur. For example, this value 2, 1 means a value of 2 occurs on the first die and a value of 1 occur on the second die. Okay. For the random experiment of rolling two dice, there can be many events. For example, getting a let's say sum of 12 having a single outcome, that is 6 6. Getting a sum of say 4 having 3 possible outcomes. You can see we can get a value of 4 if we get a value of 1 3, 2 2 and 3 1. Another event can be getting a number say less than 3 on both dice, having 3 possible outcomes, 1 1, 2 1 and 1 2. I hope this is making sense to you all. And for completeness, my dear students, let me give you a machine learning related example as well. And for this you can consider the famous Titanic dataset having 891 rows or observations and 15 columns. It shows the information of the Titanic ship that sank in North Atlantic Ocean in 1912 after striking with an iceberg. Well, this is a very famous dataset used for classification. You can see the output label survived over here in the very beginning, with 2 possible values, one showing that the passenger survived and a 0 showing that the passenger died. Based on these 13 input features of a passenger. Well, in this scenario, a random experiment can be performed on this dataset that can be randomly selecting a passenger and finding his or her maybe P class or maybe the gender or maybe the age. Excuse me. Well, the trial is performed once. The sample space for this random experiment, that is selecting a passenger and finding his or her P class, the sample space can be the unique values under this P class column, which is the third class, first class and second class, that is first, second and third class, 3 possible unique outcomes that can be there in this P class column. And one of the possible outcome, which is the result of a single trial, is getting say 1 over here, that is the first class. The outcome may be 2, the outcome may be 3 as well. Finally, there can be more than one event. There can be many events from this random experiment. Getting a passenger belonging to P class 2, having a single outcome as shown over here. Another event can be getting a passenger not belonging to P class 3, having 2 possible outcomes, first class or second class passenger. Well, my dear students, in machine learning, most of the time we deal with multiple events, and for that we need to understand 3 probability techniques: marginal, joint and conditional probabilities. And let us understand these with examples, and let me start describing with the most basic one, that is the marginal probability first. Well, marginal probability is the probability of a single event occurring independent of the output of other events. Let us consider a scenario of tossing a fair coin 3 times. The sample space consists of 8 possible outcomes represented in this tree diagram on the right. The probability of getting exactly 2 heads is 3 over 8. As you can see, there are 3 outcomes having exactly 2 heads from here, that is head, head, tail, head tail head and tail head head. Similarly, the probability of getting 3 consecutive heads is 1 over 8, and the probability of getting at least 2 heads is 4 over 8. And since we are calculating the probability of all these 3 events separately or independently as a single event, so these all are called marginal probability. Similarly, this example shows an urn containing 2 red, 3 green and 5 blue balls. If a single ball is drawn at random with replacement, of course, the marginal probabilities of the 3 events are calculated as shown over here by dividing the number of favorable outcomes with the total number of outcomes in the sample space, which is 10 in this case. I hope this is making sense. And this example 3 computes marginal probabilities of different events of drawing a single card from a standard deck of 52 playing cards. I hope this is piece of cake. Well, my dear students, here is another example of a random experiment of rolling 2 fair 6-sided dice. This left table shows a sample space with each outcome as a 2-value tuple. This first number showing the number that turned up on die 1, while second number showing the number that turned up on die 2. Note there are a total of 36 possible outcomes in this sample space. This right table also shows the same sample space, but over here the outcome is the sum of the 2 numbers having 11 unique outputs, but same 36 possible outcomes. Well, now consider an event A which is getting a sum of 3 on the 2 dice. If you closely observe these tables, there are 2 possible outcomes, that is this 2 1 and 1 2 out of 36 possibilities that sums up to 3. So the probability of A is 2 by 36. Similarly, event B is getting a sum greater than 9, and there are 6 possible outcomes like this 4 6, 5 5, 5 6, 6 6, 6 5 and 6 4. So these are the possible outcomes where we are getting a sum greater than 9, which sums up to 6. So 6 over 36, this is the probability. And finally, the probability of getting an odd sum is naturally 18 over 36. I hope this, with these many examples, the concept of marginal probability is clear to you all, which is the basic of all the 3 types. And before describing joint and conditional probability, let me spend few minutes and give you the concept of random variable and probability distributions. Well, in the context of probability, a random variable is not a variable, rather is a mathematical function that assigns a numerical value to every possible outcome of a random experiment. It is called random variable because its value depends on the output of a random experiment. And this image over here shows the random experiment of tossing a coin having 2 possible outcomes in the sample space, that is heads and tails. For heads, we assign a value of 1 to the random variable x, and for tails we assign a value of 0 to the random variable x. Therefore, x is a random variable that takes on 2 possible values of 0 or 1 depending on the outcome of the coin flip. And the probability of x equals 0 equals 1 by 2, and probability of x equals 1 over 2 shown in the bottom part of this screen is the probability distribution of flipping a coin, which actually tells us the probability of all possible values of a random variable, and these probabilities sums up to 1. Since in this scenario this random variable x can take just 2 values, so we just have these 2 values over here. Well, my dear students, a random variable can be of two types, discrete and continuous. A random variable can take on the discrete values like 1, 2, 3, 4 and so on and are counted. On the contrary, continuous variable can take on infinite number of possible values as outcomes and are measured. An example of discrete random variable is the number of customers that enter in a shop on a given day. Similarly, an example of a continuous variable is the weight of a certain animal like dog that can be maybe 30.5 pounds or 42.96 pounds, etc. Please do read more examples of discrete and continuous random variables mentioned over here. And let me move ahead to the concept of probability distribution of a random variable, which tells us the probability of all possible values that a random variable can take. And as per the type of the random variable, once again it can be discrete or continuous. Well, a discrete probability distribution can be expressed or described by a formula called the probability mass function and can be graphically represented by a bar chart or histogram where the probability is represented by the height of the bar. Some common types of discrete probability distributions are Bernoulli, binomial, multinomial, uniform and Poisson. And this left graph over here where my mouse is hovering shows the binomial probability distribution of sum of two dice. My dear students, similar to this discrete probability distribution, every continuous probability distribution can be expressed or described by a formula, but this time it is called probability density function, represented as PDF, and can be graphically represented by a curve where the probability is represented by the area under the curve. Some common types of continuous probability distributions are Gaussian, log normal, exponential, students T and chi-square distributions. And this right graph where my mouse is hovering right now is a bell-shaped curve which shows the Gaussian distribution of a continuous random variable. Well, a detailed discussion on the types of these distributions is beyond the scope of today's session. However, for a bit better understanding of this concept, let me give you a simple example of probability distribution of a discrete random variable. And consider a random experiment of rolling two dice together. The sample space is shown in this right table, but over here the outcome is the sum of the two numbers having 11 unique outputs. The random variable over here is the plus function that map the two valued tuple in the left table to the corresponding value in the right table. Now this table over here in the left bottom, having just two columns, shows the discrete probability distribution of this random variable x. Note that the left hand column in this table shows the unique sum of the two dice, and the right hand column tells us the probability of that value. I have rounded these values for easy interpretation. Well, a better way to visualize the values in a probability distribution table is by using a histogram or bar chart, which displays the values of the random variables along the horizontal axis. So we can easily see that the probability of getting a sum of 7 is maximum. The height of this bar is maximum. This is around 0.17, I think. And over the vertical axis we have the probability of these. The probability of getting a sum of 2 and 12, this is minimum, which is roughly 0.06. And one of the important characteristics of a probability distribution is that all the individual probabilities must add up to 1. And you can verify by adding all these 11 probability values from the second column of this probability distribution table. This will add up to 1. Okay, I hope this makes sense to you all. Well, I think that is enough of discussion on the concept of random variable and probability distributions. Let's once again fall back to the discussion of marginal, joint and conditional probabilities. We have seen many examples of marginal probability, which is the probability of a single event occurring irrespective of the outcome of other events. And next in the line is joint probability, which is the probability of two events occurring simultaneously together. Well, if this capital X and capital Y are two random variables shown in green over here, then probability of capital X equals X, comma capital Y equals Y is the probability that X takes the value small x and Y takes the value small y at the same time. I hope this notation is clear to you all. Before we do lots and lots of examples of joint probability, let me differentiate between now the types of the events, because now we have more than one event, so they have certain types which I will like to revise before moving ahead. And let me differentiate between mutually exclusive and not mutually exclusive events first. Well, mutually exclusive events are events that cannot occur at the same time. For example, if a die is rolled, the two events of getting a 3 and getting a 5 are mutually exclusive, that they cannot occur at the same time. The probability of one or the other event occurring equals to the sum of their probabilities. On the contrary, non-mutually exclusive events are events that can occur at the same time. For example, if a card is selected at random from a deck of 52 playing cards, the probability that the card is a queen or the card is an ace are not mutually exclusive, as both these events can happen at the same time if the card is if the randomly selected card is a queen of hearts. Okay, so one event can be the card selected is a queen and the other event is the card selected is of type heart. Well, the probability of one or the other event occurring equals to the sum of individual probabilities minus the probability of intersection of the two events. So this is the formula for not mutually exclusive events. And these two formulas shown in magenta color over here are known as addition rule of probability, which are used to find the probability of at least one of the two events occurring. So addition rule is used to find the probability of at least one of the two events occurring. I hope this makes sense. Similarly, my dear students, after mutually exclusive and not mutually exclusive events, let me now differentiate between independent events and dependent events. Well, two events are said to be independent when the occurrence of one event does not affect the occurrence of the other event. For example, if a coin is tossed and then a die is rolled, the outcome of the coin tossing is in no way affecting the probability of rolling the die. So rolling the die and tossing a coin are two independent events. And the probability of two independent events can be calculated by multiplying the probability of the first event with the probability of second event. On the contrary, two events are said to be dependent if they happen one after another and the occurrence of one event does affect the probability of occurrence of the other. For example, drawing two cards without replacement from a deck of playing card. And of course, the probability of drawing the first card do have an impact on the probability of drawing of the second card. particularly if this is done without replacement. Well, anyways, the probability of two dependent events can be calculated by multiplying the probability of first event by multiplying the probability of first event with the probability of second event, given that first event has occurred. So this is probability of A and this is probability of B given A. I will talk about this in detail when I will be discussing the conditional probability. For the time being, remember these two formulas shown in blue color over here are known as multiplication rule of probability, which are used to find the probability of two events occurring in sequence, that is, one after another. I hope this is clear. Let me now go through some very basic examples of calculating joint probability for independent and dependent events. Suppose an urn contains 2 red, 3 green and 5 blue balls. The marginal probability of getting a red ball is of course 2 by 10. Getting a green ball is 3 by 10 and getting a blue ball is 5 by 10, because there are 2, 3 and 5 red, green and blue balls, and the total number of balls in this urn are 10. Let's talk about the joint probability now. Suppose two balls are drawn at random, one after another, with replacement. The probability of selecting a blue ball and then a red ball is simply the product of the two marginal probabilities, that is 5 over 10 multiplied by 2 over 10. That comes out to be 1 over 10. And these first three questions deal with the joint probability of independent events. These events are independent because the second ball is drawn after the first ball, but the first ball is replaced before you draw the second ball. So the two events become independent. Once again, over here, suppose two balls are drawn at random, one after another, but this time without replacement. Now the probability of selecting a blue ball and then a red ball, and then a red ball, is the probability of selecting a blue ball, that is 5 over 10, and probability of red ball, given that the blue ball is already drawn. So now we do not have 10 balls in this urn, rather we have 9, and the total number of balls which are red is still 2. So the probability of a red ball, given that the blue ball is already drawn, is 2 over 9. My dear students, please make time and see how the count of favorable outcomes and sample space change when you draw two balls with replacement. Okay, well, please stop the video and try solving these two examples that compute joint probability of dependent events. Let me just move ahead, they are simple. Let me describe this example of independent events from two random experiments. On the left over here, this image, you can see a tree diagram showing the sample space when a coin is tossed 3 times, having 8 possible outcomes. On the right over here, you see the sample space of rolling 2 dice and taking the sum of the two numbers, which is shown in this table. Okay. Now, event A is getting exactly 2 heads on the coin, whose marginal probability comes out to be 3 over 8, because you can see over here there are 3 outcomes in this left sample space having exactly 2 heads. Event B is getting a sum of 5 on the dice, and in this table over here you can see 1, 2, 3, 4. There are 4. Yes, 4. 1, 2, 3, 4. There are 4 outcomes whose sum is 5. So the marginal probability of event B comes out to be 4 over 36. And finally, since these two events are completely independent, therefore their joint probability is computed by taking the product of the individual probabilities, which comes out to be 0.04166. I hope this is making sense. Simple. Okay. My dear students, let us do another example. The random experiment is the rolling two fair six-sided dice. The random variable is the sum of the two numbers that appeared on the two dice with the sample space shown in these two tables. Event A is getting a sum of greater than or equal to 5, and that is getting a sum of 5, 6, 7, 8, 9, 10, 11 and 12. Event B is getting an even number, that is 2, 4, 6, 8 and 10 and 12. Okay, how this makes sense? Let me use Venn diagram and contingency table this time that help compute different types of probabilities. And right now we are more interested in calculating joint probability of these two events, that is probability of A intersection B. Let me start with the Venn diagram first, which is shown in the right bottom of the screen. A Venn diagram is actually a figure with one or more circles inside a rectangle that describes logical relations between events. The rectangle represents the entire sample space. Over here, event A is getting a sum greater than or equal to 5, having 30 possible outcomes, while event B is getting an even sum having 18 possible outcomes. Moreover, you can see there are 14 outcomes that fall in both A and B. You can see this intersection area of the two circles. For example, a sum value of 6 is greater than equal to 5 as well as an even number. So this will fall in event A as well as in event B. And finally, there are two outcomes, that is a sum value of 3 which is neither greater than equal to 5 nor is an even number. And there are two outcomes of sum 3 over here in this table, this 3 and this 3. So these two 3's neither fall in event A nor fall in the outcome of event B. So therefore we have a count 2 which is outside both the circles in this Venn diagram. My dear friends, one more thing about Venn diagrams is that the data or values shown inside can be the frequency count as shown over here, or can be the outcomes of the events as well, or maybe the probabilities even. Moreover, before I move on to this contingency table, this intersection portion of Venn diagram tells us that event A and B are not mutually exclusive. And also they are dependent events, because if we know that event A has already happened, then the sample space for computing the probability of B will be reduced to, I think, 16 plus 14, that is 30 instead of 36. I hope this makes sense. I will talk about reduction of sample space in more detail when we will talk about the conditional probability formally. Let us now move on to this contingency table now, which is also known as a cross tabulation or cross tab. It is normally a table in matrix format that provides a basic picture of the relationship between two random variables. The rows and columns of this table display bivariate frequencies of categorical data and is useful in calculating joint, marginal as well as conditional probabilities. Right now along the rows we have event A, and along the columns we have event B. You can swap them as well. And this value 14 tells us that there are 14 outcomes that are greater than equal to 5 as well as even. This value 16 over here, this tells us that there are 16 outcomes that are greater than equal to 5 and are not even. And this value 30 is the sum, that is 30 out of 36 outcomes belong to event A. And similarly these two values 4 and 2 are the count of outcomes that are less than 5 and are even and not even respectively. Okay. Now given these contingency table or this Venn diagram, let us see how we can calculate different probabilities quite easily now. Well, we can calculate the probability of A by dividing 30 by 36. The probability of A, the favorable outcomes total is 30 and the total number is 36. Simple. And the probability of B by dividing the count of even outcomes, that is this 14 by 36. Okay, I hope these two marginal probabilities are clear to you. And to calculate the probability of at least one of the two events occurring, that is probability of A union B, is obtained by dividing the sum of frequency count of event A and B, that is this row 14 and 4, this column 14 and 4, this 14 and 16, that is 30, and this column 14 and 4, this is 18. So we need to add 4, 14 and 16. And remember, this value 14 is common to both events and you need not to add it twice. This is important. So that is why this formula actually subtracts this probability of A intersection B. I hope this is clear to you all. Finally, we can use the multiplication rule for dependent events to calculate the joint probability, that is probability of A times probability of B given A. And of course, I will talk about this conditional probability in detail a bit later when we will discuss conditional probability. For the time being, I think these marginal probabilities and joint probabilities are clear to you all, and how we can compute them easily using this contingency table. And finally, my dear friends, this is also the contingency table that shows the probability of instead of frequency counts, we have probability values over here. And this is of course obtained by dividing all the values in this above table by 36. That is the total outcomes in the sample space. So this 14 divided by 36 is 0.389, and which is the joint probability of an even number greater than equal to 5. And this 0.444 is obtained by 16 divided by 36, and this is the joint probability of an odd number greater than equal to 5, and this 0.11 is the joint probability of an even number less than 5, and finally this 0.056 is the joint probability of an odd number less than 5. Okay. Well, collectively these four cells contains information called joint probability distribution. So we have four joint probabilities: 0.389, 0.444, 0.111 and 0.056 of the two events A and B, and of course these add up to 1. From this contingency table we can also get the marginal probability, called as such because it is in the margins. So this 0.833 is the probability of getting a number greater than equal to 5, and this 0.167 is the probability of getting a number less than 5. And these two values in blue column are the marginal probability distribution of event A, which also sums up to 1. And similarly, these two values in this green row are the marginal probability distribution of event B, which also sums up to 1. Great. Well, my dear friends, I think you are well equipped now to do this example 6 at your own. From the given information, you need just to construct the Venn diagram and contingency table first, and then calculate the joint and marginal probabilities as well. As you should also calculate the joint and marginal probability distributions. And the scenario is that a class contains a total of 100 students. 70 out of them like mathematics, 60 like physics, and 40 like both. Well, event A is that a student selected at random like mathematics. Event B is that the student selected at random like physics. Please pause this video and do it at your own. And here is the solution. I hope you have done it. You have paused the video. But anyways, you can verify your solution from here. Do note that the two events are not mutually exclusive and they are dependent as well. And finally, this second contingency table shows the four joint probabilities in the gray cell, that is 0.4, 0.3, 0.2 and 0.1. The two marginal probabilities for event A in this column with blue background, 0.7 and 0.3, and the two marginal probabilities for event B in this row with green background, that is 0.6 and 0.4. Please do understand and verify your answers, and I'm moving ahead. Okay, my dear students, this time in this example, let me load a toy dataset. Let me load a toy dataset from a CSV file and calculate the joint and marginal probabilities. And to load the dataset, we first need to import NumPy and pandas. Let me do that. Import NumPy as NP. And let me import pandas as PD. Done. Let me say PD dot read CSV. So this is the method read CSV, and I need to pass the file that is datasets. Inside datasets directory, that is sample1.csv. Fine, and let me receive this in a data frame, and let me show that data frame. Let me run it. Great. So this data is a toy dataset, is a survey of Netflix subscribers to determine their favorite movies. I have just cropped the main dataset, and right now it is having just two columns, movies and gender. Both are categorical columns. This movie column has three unique values: Titanic, Braveheart and The Terminator, the three movies name. This gender column naturally has two unique values, female and male. My dear students, let's say that X be a random variable associated with the movie column and can take three unique values, and let capital Y be a random variable associated with the gender column and can take two values. And since this is a small data set having just 12 rows, so you can easily count and construct the two contingency tables, one having the frequency count and the other showing the probabilities. Excuse me. But let me get help of the pandas cross tab method for this purpose to construct a contingency table. And let me say pd dot cross tab, and I just passed two arguments to this index. To the index argument I am passing just movies column, and to the columns method I am just passing the gender column. You can get help about this, the various arguments of this cross tab. Do make time and study these. For the time being, just let me execute and show you the error, of course. So cross tab df movies columns is equal to df gender movies. It is not movies, it is movie. Okay, great. Well, so we have our contingency table with the movies along the rows and the gender information along the columns. And if you want to add the total column over here and over here in the bottom, as we have seen in our contingency table before, you can set the margins argument of cross tab method to true. By default it is false. Let me do that. Let me just copy paste this and let me say margins is equal to true. Let me execute it. Great. Now you can see the total column. So we have a total of 12 observations of Netflix subscriber, out of which 5 are female and 7 are male. 3 like the movie Braveheart, 4 likes the movie Terminator, and 5 like the movie Titanic. Moreover, there is only 1 female subscriber who liked the movie Braveheart, while there are 2 male subscribers who like the movie Braveheart. I hope this is making sense to you all. My dear students, finally, to construct the contingency table with the joint and marginal probabilities instead of these frequency counts, we can simply divide all these values by the total number of observations, that is 12. 1 over 12, 2 over 12, 3 over 12, and over here as well. But Python comes for our rescue again. Let me just copy paste this code and give it another argument, and that is normalize, and pass it value all. Great. Well, the default value of normalize argument is false, so you have to set it to all. So this is also a contingency table, but this time it do not contains the frequency as above, rather the probabilities, which have been calculated by dividing all these values with the total sample space, that is 12. This last column all displays the marginal probabilities for random variable x. The probability of liking the movie Braveheart by a randomly selected subscriber is 0.25. Probability of liking Terminator is 0.33, and probability of liking Titanic is 0.416. So Titanic wins. And these 3 probabilities are the marginal probability distribution of the random variable x, which of course sums up to 1. Similarly, the bottom row over here, this row of the table displays the marginal probabilities of the random variable y. So if you randomly select a subscriber, the probability of that subscriber being female is 0.416, and probability of that subscriber being male is 0.583, and these 2 probabilities are the marginal probability distribution of the random variable y, that is gender, which also sums up to 1. And finally, these 6 probabilities, 1, 2, 3, 4, 5, and 6. These 6 probabilities inside are the joint probabilities of the 2 random variables x and y, and these 6 values are together the joint probability distribution, and their sum is also 1. For example, this 0.0833 is the joint probability of a randomly selected subscriber of being female and like the movie Braveheart. And similarly, this joint probability 0.166 is the probability of a randomly selected subscriber of being male and at the same time liking the movie Braveheart. In the same fashion, you can interpret the remaining 4 joint probabilities as well. And let me move ahead. And here is one last example for before we close with the joint and marginal probabilities. To save time, I have already written the code. This is the same famous Titanic data set that I have already discussed. I have executed and loaded it in a data frame df, and let x be a random variable associated with the p class of a Titanic passenger and can take the values 1, 2, and 3, and let y be a random variable associated with the survived status of a Titanic passenger and can take the values 0 and 1, just 2. The total number of observations are 891. Here I have used the pandas cross tab method to construct the contingency table as we have done in previous example. Great. This cell value 80 tells us that there are 80 passengers who belong to P class 1 and do not survived. This 136, this tells us that there are 136 passengers who belong to P class 1 and survived. You see, survived. I hope this makes sense. Well, instead of count to display the joint and marginal probabilities, use the normalize argument. You can use the normalize argument. We haven't used it here. Over here. Okay, fine. So now I've used the normalized argument. And now this value 0.0897 is the joint probability of a randomly selected passenger who belongs to P class 1 and did not survive. And this value 0.133, let's say this value 0.1335 is the joint probability of a randomly selected passenger who belonged to P class 3 and survived. Similarly, you can interpret the rest of the joint probability as well. And this last column over here having two probabilities, that is 0.616 and 0.3838, is the marginal probability distribution of the random variable survived. And this last row having three probability values is the marginal probability distribution of the random variable P class. I hope this is making sense to you all. Great. Okay, fine. My dear students, after doing so many examples along with the Python code, I hope the concept of marginal and joint probabilities is crystal clear to you all. Let's dive into the third and the most important probability type, and that is conditional probability, which is the probability of an event occurring given that another event has already occurred. Let me start by giving you an intuition using this image. The upper Venn diagram shows two events of our interest, cloudy and rainy, having an intersection or overlapping area shown in yellow color. And these two events are of course dependent, as the probability of clouds in the sky does have an impact of probability of rainfall and vice versa. Now consider this left Venn diagram. Suppose we know that the weather is cloudy. This information is known to us. The weather is cloudy. What is the probability that it is also raining? And this is written as probability of raining given that it is cloudy outside, and is equal to the overlap area of two events divided by the cloudy area. So in the denominator, instead of the entire weather sample space, we have the area of the cloud event only. So the probability of rain given that it is cloudy is equal to the joint probability of rain and cloud divided by the probability of cloud, which is the event that has already occurred. I hope this makes sense. Now consider this right Venn diagram and the mirror question, saying that if we know that it is raining outside, what is the probability that it is also cloudy? So this information is given to us. This is written as probability of C given R, or probability, find the probability of being cloudy given that it is raining, and this is equal to the overlap area of the two events divided by the rainy area only, and this is equal to the joint probability of two events divided by the probability of rain, which in this case is the event that has already occurred. Great. Okay, so after this intuition, let's do some examples to understand this conditional probability. Okay, suppose three unbiased coins are tossed, and the question is, what is the conditional probability that at least two coins show heads, given that at least one coin shows head? My dear students, whenever you read such questions, they are in English and seems Greek to you, the best approach I think is to draw the sample space the entire sample space and the sample space of both the events. Well, the total sample space shows 8 outcomes. This event A having at least 2 heads has 4 outcomes, while event B having at least 1 head has 7 outcomes. I hope this is clear to you all. We have done it before as well. The number of favorable outcomes for event A are 4, and the number of outcomes in the reduced sample space of event B, which has already occurred, is 7. Therefore, the probability of A given B is 4 over 7, 4 divided by 7, which comes out to be 0.5714. So instead of dividing by 8, we are dividing by the reduced count of the sample space because of the already known information to us, that is, event B has already happened. And similarly, to calculate the probability of event B, given that event A has already occurred, is 4 divided by 4. The intersection count is same, however, this is 4, the 4 in the numerator. However, the reduced sample space is of event A now, that has already occurred, that is 4. So probability of B given A comes out to be 1. Okay, I'm sorry for this disturbance. I hope this example 1 is clear to you all. Let me move on to another example. Okay. Suppose two fair 6-sided dice are rolled. Event A says that the number on first die is 2, so the favorable outcomes of this event are 6 as shown. Event B says that the sum of the numbers on 2 dice is less than or equal to 5, and the favorable outcomes for this event are 10 as shown over here. I hope this is now very clear to you. We have been talking about this random experiment many a times in today's session. Well, to calculate the probability of event A, given that event B has already occurred, this is equal to the intersection count of the outcomes, that is 3, divided by the reduced sample space, which is the number of outcomes of event B, and this time it is 10. So 3 over 10. This comes out to be 0.3. And similarly, to calculate the probability of event B, given that event A has already occurred, is equal to 3 divided by 6, where 6 is the reduced sample space, that is the number of outcomes of event A, 1, 2, 3, 4, 5 and 6. My dear friends, you can calculate the conditional probabilities using contingency table as well. I hope from this above right table over here, this table, you can construct this contingency table. You can see along the rows we have 2 possible values of event A, that is D1 equals 2 and D1 is not equal to 2. Along the columns we have 2 possible values of event B, that is sum is less than equal to 5 and sum is greater than 5. The 4 values with the grey background are the frequency count of these events. From this contingency table we can easily calculate different conditional probabilities. For example, to calculate the probability of say event A, given that event B has already happened, is obtained by dividing the intersection of A and B, that is this 3, with the reduced sample space of event B, that is 10. So to calculate the conditional probability, we now are not dividing this 3 with 36 as we used to do in joint probability. Rather, we divide this 3 by either this 10 or 6. And since over here event B has already occurred, so we are dividing this 3 by 10. And if we know that event A has already occurred, we divide this 3 by 6. I hope this is making sense to you all. Great. Well, my dear students, try doing this example at your own. Calculate the conditional probability of A given B as well as B given A using the reduced sample space for this scenario. Try constructing the contingency table for these 2 events. that is sum is 8 and sum is an even number. See how you can construct the contingency table and calculate the probabilities, which will ease your job. Let me show you the solution if I have prepared. Yes, I have. So this is the solution. Great. Okay, so one more example. Consider this contingency table containing frequency count of 200 male and female birds in a zoo having brown and blue eyes. These first four conditional probabilities are of the gender of the bird given its eye color. For example, this probability of x equals male given that y equals brown in the first line is obtained by dividing the frequency count of intersection, that is this 70, with the count of birds having brown eyes, that is 170. And similarly, this fourth line, that is probability of x equals female and y equals blue, is obtained by dividing the frequency count of the intersection, that is this 10 female blue, with the count of birds having blue eyes, that is 30. So remember, we are dividing 70 by 170, 100 by 170, 20 by 30, and this 10 by 30. And this is because the given information is about the color of the eyes, brown or blue. On the contrary, if the given information is about the gender, we do the other way around. That is, we divide this 70 by 90, this 20 by 90, this 100 by 110, and this 10 by 110. I hope this is clear to you all. Please make time to map the information from this contingency table to calculate all these different conditional probabilities. And I am moving ahead. Great. And before closing today's session, let's do an example, one last example to calculate the conditional probabilities by loading the all-time famous Titanic dataset. Once again, let x be a random variable associated with the P class of a Titanic passenger and can take values 1, 2 and 3, and let capital Y be a random variable associated with the survived status of a Titanic passenger and can take the values 0 and 1, and there are a total of 891 observations. Okay. Well, over here I am using the cross tab method of pandas data frame to construct the contingency table by keeping the survived random variable along the rows and this P class random variable along the columns. So these are the frequency counts. I have discussed while doing the joint probabilities as well. And well, to compute the joint probabilities, we divide each cell value with this total sample space, that is 891. But for here, we need to calculate the conditional probabilities. Let's first calculate the conditional probabilities of survival given the P class information of the passenger. So if it is given that the passenger belongs to P class 1, the probability of survival is 0.629. Yes, this one. So we are now dividing this 80 with 216, this 136 by 216, 97 by 184, 87 by 184, 372 by 491 and 119 by 491. We are dividing this because the given information to us is about the P class. So since we want to calculate these conditional probabilities with the given information of P class, so the cross tab method comes for our rescue to do this job by using the argument normalize. Instead of passing the value all, we pass it the value columns. Let me just execute it, and you can map the values. You see probability of survived is equal to 1, P class equals 1 is 0.62963, and you can see this 0.62963 over here. Great. I hope this is making sense to you all. Okay, so well, my dear students, in order to calculate the conditional probabilities of passenger class given his or her survival information this time, the reduced sample space for survived is equal to 0 is 549, and the reduced sample space for survived is equal to 1 will be 342. And this is shown over here. So now we will divide 80 by 549, 97 by 549, and 372 by 549. Similarly, 136 by 342, 87 by 342, and 119 by 342. And this way we will compute the conditional probability of a person traveling in P class given that she has died or not. And for that, to the normalized argument of the cross tab method, instead of passing this columns argument, I am passing index. So based on survived. Great. I hope this output is making sense to you all. Well, my dear students, I think that is enough about joint, marginal and conditional probability. We are well equipped now to understand Bayes theorem and the naive Bayes classifier in our next session, inshallah. If you have liked today's session, please subscribe my YouTube channel and share it with your friends. I wish you all the best, happy learning, and Allah Hafiz.